build up this material are as follows. So the first big topic and class of problem you're going to have to handle is the problem of how to deal with what happens when you have a known constant acceleration in a one-dimensional context. Then that's going to get us into thinking about what, where, and when type problems, but again we'll be limited to one dimension. Then we're going to go on and look at what happens in force with balances of forces as you go out to multiple dimensions, and we'll be reviewing a bit of trig as we do that. Then we'll start to apply these basic ideas and now looked at a classic set of problems in elementary physics courses, projectile problems, where now in a projectile problem you're looking at motion in two dimensions, where you're shooting a bullet or something and it kind of carries out some arc throughout space till where it finally hits its target. And that's going to build on the idea of constant acceleration, because there is a constant acceleration involved in these problems, but now you're going to be looking at motion in a two-dimensional context. So we'll then be fully dealing with accelerations in multiple dimensions. Some other applications of motion in more than one dimension that classically come up are, for instance, involved in circular motion, where now say I have some object tied on a string and it's going around some pivot around in a circle. Well, it's not traveling in a straight line, so we know there must be some acceleration. And clearly as the object is moving around, it's not just moving along, again as I just said, a straight line. It's moving around in a circle in maybe the plane of this paper. So it's a two-dimensional type of motion. Finally, there's a little extra topic tacked on, which in some sense really belongs under circular motion, but sometimes it's a little bit unfamiliar to people, so I'd like to break it out as a small separate topic, which is orbital motion. Now, satellites in orbit generally are traveling around in circular paths, so this stuff really is an application of circular motion. So those are the basic topics. Constant acceleration in one dimension, looking at force balances in two dimension, then we look at constant acceleration in two dimensions, which is basically the same thing as saying you're doing a projectile problem. We look at another type of two-dimensional motion, circular motion, which is very important and comes up in many contexts. One of those, of course, is orbital motion. Now, in terms of how to kind of study and approach these different subject areas, remember that we are going to be doing some examples coming up later on in the podcast. But just kind of an overview of how you should approach these things. I have, over the years of working with the students in this class, found sort of a step-by-step approach which really helps you to master the material and get through it. One is that, although I'm not a big fan of memorization, when you're dealing with constant acceleration problems, there really are three basic formulas that you need to be able to use over and over again. They, of course, appear on the formula sheet, but you're going to be using these so much, it's probably just worth memorizing them. Also, if you memorize them, you tend to have in your head what all the various algebraic connections are, and that makes it a little easier to pull up the right equation at the right time. I'll overview these when I do some problems in constant acceleration, but these are basic formulas such as the final velocity equals the initial velocity plus the acceleration times the time, and there are two more that are somewhat along those lines. So I'm going to suggest that you memorize those basic formulas that we'll cover in a moment. Then what I suggest students do is to read the overall problem, right? Usually these are word problems, and translate every fact that they give you. Like if they say you dropped the ball from rest, well, that tells you that immediately that the initial velocity must have been 0 because it was at rest initially. You translate all of those things into algebraic equations, into math and algebra, and then once you're looking at them and knowing what your basic formulas are, you'll be looking at an algebraic problem. And what I found is that the students in this class, their algebra is really quite good. And so once you've got it translated into algebra, pretty much you'll know what to do. Whereas if you're just reading through all the words and trying to think through what's going on, sometimes you can get kind of tripped up because that takes a lot of experience to do. Whereas if you just translate everything into algebra, which does require a lot of thinking, but once you've done that, then how to combine the things will click for you very nicely because of your good algebra skills. Then when we go to forces in two dimensions, basically this boils down to how to draw proper free body diagrams, and I'd like you to remember that I actually have a podcast on that topic. So I would suggest you take a look at that. That's separate from this podcast. It's one of the standard podcasts. And that deals a lot with how to do the forces in multiple dimensions. It's going to require you to review your trigonometry right now. So if you're not up on your trig, now is the time to really review it, because that comes up quite a lot. It turns out, though, that there's two basic formulas that are used over and over again that are most handy. And I'll review those for you when I go in detail on the examples of forces in 2 dimensions. Another little tip, which will make a little more sense when we look at those examples, is that you have a choice of how you align your x and y axes, and there's always an art to doing that. But it turns out in the end, the basic trick is to make sure one of your axes lines up with the acceleration of the object. If you do that, and do your trig like I've shown you in the free body diagram podcast, and stay organized, you'll end up with a series of algebraic equations, and then you should be able to solve them quite readily with your good algebra skills. So now for projectile problems, they really just build on constant acceleration in 1 dimension. The basic idea is the same. It turns out that x and y, the 2 coordinates, the motion in them is completely independent. So they separate really into, all projectile problems separate into 2 sets of problems. One set of facts and relations dealing with x, another set of facts and relations dealing with y. If you combine them together, you just end up with a slightly more complicated algebra, or sometimes significantly more complicated algebra. But you guys are good at algebra, and so once you've got it translated into algebra, the same approach as in 1 dimension, we got everything translated, you then go ahead and solve. And I'll do an example, show you how to do that. Finally, for circular motion, it's not really an entirely different topic. The basic idea is just that if you're moving in a circle, there's a formula, which I've copied for you here, that tells you what the acceleration is. And after that, it is application of the free body diagrams and the trig and the algebra that you will have built up in all of the previous topics. But this topic does kind of combine a lot of ideas, and there's some counterintuitive stuff to it. So it's worth studying as sort of a separate topic, and I'll do an example of that for you for sure. And then, as I said, orbital motion is really just a special case of circular motion. So the example that I'll choose so that you're covered for both circular and orbital motion will be some kind of orbital motion problem in a circle. Okay, so that sums up the basic topics and the overview. Now we're going to go on the next segment and take a look at how to handle constant acceleration problems in 1 dimension.